Okay. So, we will look into pipe network again, just again we will look into the pipe network. As I said that we have to find out the correction, but one important point is that one can Hazen-Williams equation is commonly used, but one can use other equations because they are empirical like Benning's equation as well. So, let us see how Hazen-Williams equation is one can use here for finding out the solving a pipe network problem. So, what we want to find out is correction. Now, we have assumed values, let us say our assumed value is q 0 in a branch, right, q 0 in a branch. So, assumed value is q 0. Now, since it do not sum up to 0 in a loop. So, you got to change this value and that is the correction. So, the correction is let us say delta q. Now, softwares might be available today to solve all this. So, therefore, but then we must know the basic principles because there will be softwares available. So, now I apply correction and after that it is q. So, q 0 is assumed flow rate in a branch pipe and correct or balanced flow rate is q such that q is equals to q 0 plus delta q. From Hazen-Williams equation finally, what comes is that delta h is something some sort of n multiplied by q to the power x, because q was given as hf will come somewhere divided by L hf to the power 0.54, right, hf to the power 0.54, and then you have d which is known, d to the power 2.63, d is known, c is known, constant part is also known. So, basically hf sum total of hf has to be 0. So, hf can be written as h can be written as some n q to the power x, because 0.63 is very much there, 0.54 is there, point. So, 1 by 0.54 that will come, x will be, x is nothing but, yeah. So, because 1 by 0.54 that is what it is. I think it is written somewhere, I will come back to this, I will come back to this, yeah, this is 1 by 0.54 is 1.85. So, q can be delta h can be expressed in terms of something, some constant q to the power x. So, q is the final value, right, correct value is correct value of, I want to find out delta h. So, n q 0 plus delta q to the power x, delta h means the head loss in that branch, head loss in that branch, right, correct value of head loss in the branch, that should be equals to q is the correct flow after correction. So, q to the power x, which is q 0 plus delta q to the power x. Now, this is a binomial, I can expand it through binomial expression, binomial expansion. So, q 0 to the power x, x q 0 to the power x minus 1 etcetera, 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 so on. And every time I will have delta q and then delta q square and delta q cube etcetera, etcetera. So, what I can do? I can ignore all of this, because delta q will be relatively small, So, ignoring all this part, I can find out delta q, right. So, I find out delta q, right, I can find out delta q. So, delta h 1 0 1 initially was not, first trial it was not equals to 0. Then I want to find out the correction, sum total of all this should be equals to 0. I have neglected the terms beyond the delta q square and higher terms, delta q square and higher terms I have neglected, and I have summed them up for the whole loop, and that should be equals to 0. So, let me repeat again. So, therefore, I can express and I can neglect all these terms. So, then what I am left with? I am left with that delta h in a given branch is equals to this much. Sum total of all this in a given loop must be equals to 0. It was not earlier not equals to 0, but now must be equals to 0. So, that is what I am doing. So, that should be equals to 0. So, therefore, if I expand it out, right, n I q I x etcetera, etcetera, delta q I should be able to take out of this. I am assuming the delta q correction in throughout the branch, the flow throughout every throughout the loop, throughout the loop in all the branches in the loop. That is what I have done. that is what I have done, you know. So, I have just expanded. So, delta H in a loop. So, every one I assume same correction, and that is what I am doing here. So, I can get an expression for delta q from this one, because this is equals to 0, delta q will come outside the sigma. So, this would be nothing but sigma of, you know, n I assumed values of q 0 to the power x divided by same, because this is loop specific, ith loops for ith loop, n I x to the power minus 1, this term, you know, sum total of all this term. So, delta q simply comes out to be, because if I expand this is outside the expansion, rest all are within expansion. So, just I do that and I get relationship like this, right. Now, if I divide this by q 0 I, then I get same, and in fact, the expression comes out to be something like delta. This was the delta H I which was not equals to 0, because that sum total was not equals to 0, and this is also same value, because this is sum total was not equals to 0 divided by q y of all this one. So, you know, n would be there, or x whatever the values that would be there. So, delta, you know, delta q you can obtain, delta q you can obtain. So, delta q is equals to delta h 1 point. Now, x is x to the power, because this is x was coming, x is nothing but 1.85, 1 by 0.54. So, x was coming here. So, x you can find out, and that is how you can find out the correction. Repeat this process for, you know, and when the error become too small, you know, when this is too small, the sum total is very close to 0, you stop. So, you get the corrected values of q, etc., right. So, that is how one can obtain. I do not know whether I have got an example problem here, I might have or may not have, I am not sure. Let me see if I have an example problem for this one. I might have an example problem for the loop tabular form. I will just tell you, this is normally done in a tabular form, maybe it is there somewhere, I will just check, right. But then there is some practical example. Let me see if I have some, otherwise, okay, I might be having, I will just check, but let us take some practical. So, this is the basic principle, right, this is the basic principle. I must be having a example problem sometime related to this. So, this is the basic principles, right. Okay. So, that is the basic principle of pipe network. Okay. First thing is, now let us look into some of those issues related to design. So, first you draw the pipe work layout, right, like this, maybe it is there somewhere it is there. Yeah. So, you know the water tank, every detail of it is known, and the pipe work layout you draw. So, you draw the, maybe it is somewhere there are many of them like that. So, this is an example case. So, I just want to highlight the pipe layout, it would be there somewhere. Yeah, this is like this, something like this, you draw the pipe layout basically. So, this is one floor, this is another floor, how many wash basin, water closet, bath, etc. for each one of them. So, that you draw out, and distance you find out, the pipe length. So, you draw the pipe layout, right, that is the first thing you do. First thing you do is that. Okay. So, draw the pipe work layout. Identify the fixture units appropriate to each fixture or each fitting, right. Sum the all fixture units at all pipe, you know, for all of them, and calculate sum total. Convert this fixture unit to discharge from graph from National Building Code, or obtain the effective number of fixture table. There is a table also given, graph is also given. So, you can get from the table. Now, one fixture unit corresponds to 28.3 liters. The discharge from one fixture unit is 28.3 liters. So, if you know the effective number of fixture units, what is the Q, that you can find out. Your aim is to determine the D. your aim is to determine the D, and D would generally be same, but if it is different then again series network. So, convert this one either or find out effective fixture unit 28.3 liters multiplied by 28.3, that is the flow for any pipe, any branch pipe you can obtain. Find the head of water causing the flow in each floor, because you know that there is a, supposing it is a tank supply, from the tank what is the head available, and how much is head available at a given flow level, because it will be this much. If there is a pipeline here going, the tank is somewhere there, this will be the head available head, right. Length will be of course, and if there is a loss here, let us say it is a shower. So, another 2 meter reduction or 1 meter, whatever the height, that reduction will be there, but length of the pipe would be total. So, that you have to see. So, from head of water causing flow in each floor, that you can find out. Estimate the equivalent length of the pipe. Now, equivalent length of the pipe takes account of losses. One way is to increase them by 30%, because there will be bends, losses in bends. So, meter losses of course directly you can calculate out, but something like 30% is frictional losses in resistance of bends, tees, steps, etc., etc. The loss of meter you can again find out directly. So, water meter is there from the municipal line as soon as you enter into the consumer area. There is a water meter, right. Now, this water meter, loss in water meter, that is given in a table, it is given in a table, and you can take it from there itself. Size of the water meter, pipe size will dictate the water meter size, and that is for a given pipe size, what is the loss, meter loss, that is also given. Now, index circuit is that circuit where the HF by L is is lowest S, because that would dictate the size of the pipe, lowest S. Diameter will be maximum when S is least. So, you select that index pipe whose gradient is less, because you are not going to change the pipe diameter. In every floor you are not going to change the pipe diameter, right. So, in the floor the pipe diameter will be same, and other floor also it will be same. Main might be different. For example, if you have a sprinkler system for firefighting. Now, there is a main riser, if you remember, we said that there is a main riser and there are branches. Now, main size could be different, because you will connect to so many branches, but each branch connecting to the sprinkler head, they will be of the same size. Although, supposing there are one pipe might have a few more sprinkler, but it is not worthwhile changing. That is what we do in all engineering design. We have discrete decisions are you have discrete values of your design variable. When you are dealing with pipe, structural sizes and so on, you have discrete values, say steel built already produced one, factory produced material. Molded material you can have your choice, but if it is a factory produced material, pipes, rolled section, steel IS, medium beam or heavy beam, ISMBs, their sizes are fixed. So, what you do? You tend to use similar sizes as much as possible because of other reasons, unless there is a significant economic reason. It's a similar example analogy is columns in RCC columns in a given floor. You might group them and you might have 3 sizes, although some of them load carrying capacity required would be quite different for each of the column, but you do not change them, because shuttering cost will eat away the the benefit that you will get from the materials reduction. Similarly, here many other costs will involve, and that will eat away. So, therefore, we do not do it, you keep it same. So, that is what it is. So, this is the circuit loss gradient. Ensure pipe sizes, might use Hazen-Williams equation for the flow, estimated the S for the index circuit, and using that you find out, determine other pipe sizes if required from S and Q for appropriate branch. So, that is the procedure. Now, just the graph from the code is reproduced. For small values of total fixture units, flush tanks with flush bulbs, right. This is is a dominant flush bulbs or with flush tanks, possibly these days more of this. So, probable demand is given, and in fact total fixture unit when there are a large number of them, both both coincides, both situation coincides, and probable demand is given in probable demands are given. So, I mean I am just showing the curve, you can refer to them if you like, or you can calculate from a table as well. There is a table also. So, example, let us take up an example problem. Let us say, supposing you consider a 4-story building, ground floor plus ground floor, right. So, 4-story plus ground floor, and story height, just for the sake of ease we have taken it to be 3 meter. Water tank is supported over the terrace on columns at height 3 meter. So, additional 3 meter height has been there. The fixture in each apartment, so it is a residential complex, each apartment consists of a sink and a tap kitchen, let us say, a overhead flushing tank in WC, one ablution tap, one shower tap and one wash basin in the bath with mini geyser in the bath. There are 2 apartments per floor. Elevation of highest fixture, that is your shower, is 1.95 meter. So, in fact, in a floor you will have double, because there are 2 apartments. There are 2 apartments. Made it simpler, something like this. I have a water tank 3 meters, so each floor is 3 meter, right. This is the example, okay. And this is what taken from the table. Kitchen sink is given, fixture unit equals to 2, to have a feel for you. Ablution tap is taken as the least, which is 1. Supply of overhead flush tank supply, because that goes slow. Shower 2, wash basin it is taken as 1, the minimum. Geyser is 2, etc., etc. So, something like that. So, this is the now how many numbers are there? Yeah. So, 13 fixture units in an apartment. I have one kitchen sink, 2 fixture unit, kitchen tap, 2 fixture units. So, if I sum them up I get 13. Since there are 2 apartments, how many there will be? 26 fixture units. For 26 fixture units, effective fixture units from table 32 of SP 35 gives you, it has to be interpolated between, because fixture unit is 26 between 20 and 30, right, 20 and 30. For 20 it is 2, 20 it is 2, okay, and 6 is extra, 6 by 20, 3.3 minus 2. So, for 30 it is 3.3. For 30 fixture unit, the table gives you effective number of fixture unit to be taken as 3.3. For 30 it is 3.3, right, and for 20 it is 2. So, 22, 30, 3.3. The difference is 3.3 minus 2 to be distributed over 10. So, multiply, so 6 divided by 20 into 3.3, etc. So, you can get actually about 2.4, it comes out to be 2.4, right. 2.4 is a fixture unit by doing a simple interpolation between the 2. 2 for 20, additional for 6, right. So, that is how we find out. Okay, okay. So, that is the total number of fixture units. Flow rate is 28.32 liter, that is given. So, for 2.4 fixture unit, 68 liters per minute. So, it is given as 2.382 liters per minute. So, it will be 68 liter per minute, and then you can convert this into kiloliter per hour and per day if you require to use the same formula, right. So, kiloliter discharge, okay. Meter loss is given for 25 millimeter size, meter is 4.5 meter. This again given from another table, So, this is 4, this is 68 into 60, 68 into 60, this was liter per minute, I want to convert into hour. So, this will be 4.080 kiloliter per hour, right, and this 4.080, 4.080 kiloliter discharge. Meter loss is 25 millimeter, right, and this is given in a table 4.5 meter. So, now for ground floor available head. So, if I go back to this diagram, for ground floor 3, 3, 3, 3, 3, 15, right, minus the meter loss, 15 minus meter loss minus 1.95 would be there. So, 15 minus 1.95 minus meter loss 8.55, that is what it is, right, for ground floor. 3.5 is 15 minus 1.95 minus 4.5. This one
For 26 fixture units, effective fixture units from table 32.
is 2.4.
That is coming out to be 2.78.
Then it must be, one is to see, I do not know exactly 3.3, 3.34, 3.34, or it might be for 40.
Yes.
It might be for 40. So, whatever the value is, actually this it might be for 40, this might be for 40, right, this might be for 40. Yeah, because I am dividing by 20,
Yes.
I am dividing by 20, so it is for 40.
It should be 40.
40, 20 dividing by 20. So, for 20 the change is 3.3 minus 2. For 1 the change is 3.3 minus 2 divided by 20. For 6 the value would be 6,
It should be 40.
40. So, 3.3 corresponds to 40 from the table. So, anyway, this is the head available head. So, what is the maximum length? The length of the pipe from ceiling tank is 12 plus 2, loss 2 is again another 30% you take, or whatever 2 values, so this is 14 meter. If you look at this, how much it would be from tank 3, another 3, another 3, another 3. So, make it 4, 3. So, it is somewhere here, right. So, we are trying to calculate out the length of the pipe up to the ceiling from tank, ceiling 12 plus loss in fitting is 14. So, up to ceiling level is this at 8.55 divided. So, S comes out to be this, flow rate is 97.28 kiloliters, that is 68 into 60 divided by 1000. How does it come? Kiloliter per day, flow rate was 68, right, 1000 into 24 hours, yeah. So, multiplied by 24 hours, so kiloliter per day we want to calculate out, per hour to per day. This comes out to be 4.0 something multiplied by 24. We calculated this out to be 4 point, how much? 4.080 kiloliter per hour. Multiply this by 24. How much it will come to? 97 or something. It comes to 97 point something. 97 point something, 97.92, 98 kiloliter per day. So, put it in the formula, find out the D. So, next higher size is 25 mm. So, that is it for first floor available head. You can repeat this process for other floors, and possibly if you repeat this process for other floor, you will get the pipe size nearly same. So, use 25 mm pipe in each floor. Yeah, let us see for the other floor, somewhere is coming high, 33 mm. Distribution pipes lines, sorry, each apartment would be lower size. Yeah, so that is the pipe, main pipe carrying, because I am taking from the top. So, that has to be highest of this. So, let us see the third floor, what does it give? Third floor, they repeat this process, and because the main pipeline bringing that would be of the larger size, in each branch pipe I might use a size, because this is I am this is for the main pipes I am calculating. So, corresponding to each one of them actually you can calculate out.
Sir, in third floor it is saying that since the available head is minus 0.45, so what we are going to do in that case?
Hence, overhead tank has to be raised to about the meter. So, you have to raise the overhead tank in this I just showing you the calculation procedure, but in the third floor that means you have to raise it, otherwise water is not going to come to the third floor itself. So, overhead tank has to be raised or avoid a meter, that 4.5 meter loss in the meter. So, if there is no meter you can calculate or raise the head and calculate and so on. So, repeat this process, this is the procedure, this is the procedure. Okay. A similar exercise one can do, similar exercise it is for a two-storied one. This is for a domestic water supply, a minimum same similar. So, this is shown, there is a water tank, there is a this is what the supply is. This pipeline dimension should be different than this one, because this would be head available here, the length is whatever the length you calculate out, and the head available head may be 1 meter per second or whatever the residual head. So, the difference is the head here and the length one has to see. So, the head here is created by the pump. So, again in case of floor, assign the unit fixture unit values, and same process, total 6, branch B total 4, discharge in branch A. So, if there are number of branches, there are number of branches actually, this is you might call it branch A, branch B in the floor itself, and then find out branch A and branch B, right. So, required flow is this much, this is given in meter cube per second. Effective length in branch A and B are calculated, SA and SB. Now, the idea here, why did I take this example, is to show that the one which is lower, that will dictate the design. So, that is the index. A is the index branch pipe, A is the index branch pipe, the same procedure, and this was all in meter cube. So, basic first equation was used. This is in meter cube. So, everything in basic, but if you convert everything into kiloliter per day, then the equation just changes, otherwise all same, right. To the supply to the main, effective length main is this is the main.
So, these 4, 2 and 3 are the
Distances, these are the distances here, these are the distances, spacing basically between water closets and so on and so forth. So, these are the spacing actually or distances between them. So, that is how you can calculate out, and for the branch on the main supply available head is total given as 9 meters, because 20 meter was the head from the pump at a distance 9 meter etc., and I mean the distance is given. So, for this one you can you do it separately and find out separate pipe sizes. So, that is the supply, that is the idea, right. That is how you can actually calculate out or design a pipe system in buildings, basic principles, and in fact there are obviously there are softwares available today to do all this kind of thing, but that is the basic principle. All right. So, that is related to cold water supply. Now, hot water supply system, basic principle is, I will come to this, but maybe first I look into a simpler diagram, yes, this diagram, and then we come back to this. Now, normally you have a hot water supply, you will have a loop, and wherever you have the hot water storage, right, or heater or whatever it is, hot water will be at the top and cold water at the bottom. So, your supply goes from top and then it comes back, right, it comes back, okay. It it is a loop, because otherwise pressure would be generated. Supposing I keep the tap closed and hot water, actually there will be pressure generated. So, I have to have some kind of venting or whatever it is. So, we will see that. So, that is what it is. So, this is a loop of the hot water supply system. Even if you have individual small domestic hot water supply system like geyser and things like that. So, essentially the pressure, the pressure, hot water creates pressure, and that has to be released in some manner. We will see that again. We will come back to this sometime later on. So, basic principle, the temperatures, desirable temperatures are given in the code, National Building Code gives you. Supply to the sink is 60 degree, wash basin 55 degree, hot bath as run or for use at 41 degree, and warm bath is 37, tepid bath is something like this, somewhat less. Storage temperature preferable is around 60, and if it is soft water, hard water a little bit less, soft water 65 degree centigrade, scalding temperature is 65 degree centigrade. So, this basic scheme of hot water, temperatures of hot water desirable given in the code. So, I think we will look into this just in a minute.